Hello everyone and welcome to another episode of Investigation. In today's episode of Investigation, we will go over the concept of second derivative. And this concept is actually very useful when you're trying to do stuff with second derivative. So that is the slope of the function of the slope. And that is commonly used in physics. But before that, we will go over a daily problem that is also the same problem that I went over in the end of the last episode. And of course, you can pause the video if you want to try this problem and proceed the video when you're done. And before that, I will actually point out that x to the x to the x is actually x to the, this invisible parentheses, x to the x. It is not x to the x to the x. That's different. So the invisible parentheses is actually here. So x to the x to the x. Want to find the derivative of that. And obviously the first step we're going to do is to set y is equal to this function. And we need to somehow get rid of this annoying exponent that we have to deal with over here. Of course, as we've went over in the last episode, a common technique would be to take the ln of both sides. So there will be the ln of x to the x to the x. As I've said, that is, there's an invisible parentheses here. We can just take this out. So that would be equal to x to the x ln of x. And at this point, it should be very obvious what we're going to do. We're going to implicit differentiate on this, so that is going to just be the derivative with respect of x of ln of y is equal to the derivative with respect of x to the x times ln of x, such as that. And over here, we need to use the product rule over here, and over here it's just 1 over y times the derivative of y over the derivative of x with respect of x. And this power rule we can list out. So f of x is equal to x to the x over here. So we have x to the x, and g of x is equal to ln of x. Obviously, it is very obvious that this is 1 over x, and we have this derivative. And this derivative might be a little bit harder, but we went over this in the last episode. That is x to the x times the ln of x plus 1. That is what we have over here. And we need to use the power rule over here. So, not the power rule, the product rule. That is x to the x times 1 over x plus this x to the x to the ln of x plus 1, this times the ln of x. And let's see if we can simplify this a little bit. So that what we have over here is pretty much the simplest form that we have, but we can try to simplify this a little bit. Obviously, we need to multiply that y over here, so the derivative of y with respect of x is y times this thing. That is y times x to the x of ln of x plus 1 times ln of x plus this thing. So that is x to the x. So that's x to the x times x to the negative 1, which is basically equal to x to the x minus 1 power. And if you write it as this, yeah, it should be accepted as well. So that is our final expression, and we need to plug in basically at the y that we set, because y is not actually in the problem statement, and we actually need to write it back basically, and on the left side as well. So the derivative with respect of x to the x to the x. And this is our answer. not too bad after learning the technique. And the whole point is to learn the technique, to take the natural log of both sides. And the second derivative, today's topic, is really a very easy concept that I think many of you have encountered at this point, and we're just going over like different notations of it so that you don't get worried when you actually see it on the test. The second derivative, which is basically, let's say if we have the second derivative, which is written like this, the second derivative of x, of f with respect of x, and if we have f of x, if we have g of x, that to be equal to the derivative of f of x, then the second derivative of f of x is equal to the derivative of g. Let's take a look with an example. So let's say if we have, let's get a famous physics formula. Let's say that f of x is equal to, let's say 1/2 at squared. Let's say a t squared because we usually use t in physics, squared plus v0t plus x0. And we want to find the second derivative of this. So the first derivative of that is equal to, we can just simply differentiate, that's at plus v0. So the second derivative, that's very easy as well. Just take the derivative of this, which is just equal to a. And there is a special name for both of these. That's just the position. And the slope of the position, that is the instantaneous velocity. And the change of velocity, that's just the acceleration. And there are also different notations for second derivative. One of them I've shown is the second derivative, so double prime of x, and also we can write as the derivative with respect of x of the derivative with respect to x of f of x. Although this is a pretty silly way to write it, and you probably don't want to write that. And another way of writing it would be the d squared over dx squared. Looking at this, that would be equivalent as well. Also, if you have f of x as, let's say, a y, then there's a variation of this notation. If y is equal to f of x, then we have this as d squared y over dx squared. And obviously you can do that for basically infinite amount of times and just write it as, let's say, d cube, d fourth, so d cube over dx cube, something like that. And also over here in the prime notation, if we want to take the derivative of that, we just have 3 prime of x. We can have, let's say, 4 primes of x, but you don't really want to write it out like that. Let's say if you want to take the derivative like 20 times, don't want to write it out like this. The f prime of x. That just doesn't seem realistic. So we will invent a new notation of it. Let's say that is f of x, and that we, inside the parentheses, we write the amount of time that is differentiated. Let's say 20. And that is just equal to f prime. I'll just skip some of these prime, and there's 20 primes of x. And this notation is often used when there are, let's say, more than 5 primes, but obviously you can write this f prime of x as f of parenthesis of 1, this of x, but we don't really use it, and this is more widely accepted. So that is all for today's episode of Interstigation, and I will see you in the last episode, which is coming out tomorrow, and we will go over L'Hopital's rule. Goodbye.